an assistant professor of teaching in the Department of Statistics and a co-director for the Master of Data Science program on the Vancouver campus at the University of British Columbia. In her current role, she teaches and develops curriculum around the responsible application of data science to solve real-world problems. And today she's going to talk about teaching data science and the challenge of teaching reproducibility while facing issues with motivation and challenging reproducibility tools. So thank you so much for speaking with us today, and welcome.
Thank you for the introduction, Amy, and thank you to the organizers for the invitation to speak at this really awesome workshop. The list of talks looks really cool and amazing, and I'm going to try to catch as many as I can over today and tomorrow. So for anyone who's interested in following me on Twitter, I put my Twitter handle here. And then if you're interested in the slides, this is the link to the slides here as well. Maybe I'll just quickly pop that in the chat in case anybody wants to take a look. Okay, and let's get started. So I thought I would start off with a little bit about me and what I teach at UBC. So from, I guess, position-wise, Amy already covered a couple of the things, but I also am associated with software and data carpentry. So I'm an instructor with those organizations, as well as an RStudio Tidyverse instructor. At the University of British Columbia, I teach both graduate courses and undergraduate courses. I've been primarily involved in teaching the Master of Data Science program, which is about 5 years old now. And the courses that I'm currently teaching in this program are programming for data manipulation, which is really a programming in R course, statistical inference and computation 1, data science workflows, collaborative software development. So some of these are really focused on reproducibility, the latter two in particular, and then the other, the statistical inference course is focused on statistical inference. However, we try and use reproducible tools while we teach it. In the undergraduate space, I've been teaching an introduction to data science course that I helped develop. And then my new challenge in the next year is going to be building a course on reproducible and trustworthy workflows for data science, which I'm very excited about. So the data science definition that we embrace in the Master of Data Science program at UBC and in the data science courses in undergrad that we're developing there is the study and development of reproducible and auditable processes to obtain insight from data. Now, when you go into the data science classroom, students are very excited about usually learning data science, but what they're most excited about is this second part of the definition, the insight from data part. They often aren't even aware about the reproducible and auditable processes part, and they see that more as a pain. So you have this barrier when you're teaching the reproducibility aspects of data science is that they don't know about it, A, and number two, they're not excited about it. And then we have this third challenge, which I'm going to talk to about in a minute, which is that the tools that we use for reproducibility are not necessarily smooth and easy for learning. There's usually a pretty steep learning curve associated with them. So over our 5 years of teaching these things at UBC, we found some key things that we've experienced, at least, for teaching reproducibility. So the first is that we've realized we have to place this extra emphasis on motivation. We found that direct instruction is really important and that lots of practice is really important. So I'm going to talk about each of these, why we believe they exist, or they are so, and then I'm going to give some high-level examples of how we do these and then give one specific example for each of them. So why do we need extra motivation? I think I already said that, but I'll say it again. They don't have this intrinsic excitement or motivation about the topic, and it's a challenging topic. And just to use a little bit of humor to illustrate this extra challenge, for those of you who are familiar with some of these tools, these cartoons and GIFs might be joyful. And even if you're not familiar, so this cartoon is about a version control software that's the most commonly used one for reproducibility, Git, and it's essentially it's well known, so well known. There are cartoons about how hard it is to learn this stuff, and that most people actually don't really learn it deeply, and they just try what works and get themselves into a lot of trouble, and sometimes end up in a place which Jenny Bryan from UBC and now at RStudio would recommend that you just burn it all down and start again. R Markdown is a lovely tool, but anytime you involve LaTeX into anything, you can get some very challenging error messages that aren't really clear about where they come from and what you should do next. So this is another place that students find problems. And then another tool that we use in reproducibility is containerization with Docker. And this is a really challenging one to teach and motivate students to learn because it's so different from writing code to do analysis because it takes a long time to install things. And it takes a long time to automate the process of installing things and making a compute environment accessible. And it's not that exciting because things already work on their own computer. So hopefully these cartoons have illustrated basically a lot of the motivation challenges we have with these tools. So what do we do to motivate in our classrooms? So one thing that we've used is telling stories from the trenches. So those of us who teach these courses usually have had some experience with doing research in their PhDs or postdoc or are still currently doing research. And through these are lived experiences of learning reproducibility tools and applying it to our research, we have made mistakes. Our collaborators have made mistakes, and we can share these with our students. In the Master of Data Science program, a lot of the students have work experience that may have touched on to data before. And so they also have stories from the trenches. And so in the in-person classroom, you can do some think, pair, share exercises around this and get the students to talk about their stories as well as hear your stories. And then in the Zoom classroom, you can always do breakout rooms for this sort of thing. Another example that was something that I learned from Jenny Bryan is let them fail, but let them do this in a controlled manner. So at least myself, I experienced a lot of failure in graduate school and in my postdoctoral research in reproducibility. And it took a long time and it really slowed me down. And I'll argue in a few slides later that we shouldn't do this. So if we can set up these scenarios where they feel a little bit of this pain, but it's for a short period of time, that can be very useful. This can be especially useful when you're teaching undergraduates data science because they haven't had these real life experiences. And then third is something that I'm going to try and bring into the new course that I'm developing, which are case studies of failures that have had real world consequences. And again, these are, the master students, this hasn't been as important for, I don't think, because they've had some of these real life experiences themselves at work. But for undergraduate students, again, that haven't had the opportunity to do research, don't really understand what the real world consequences are. So I think real case studies that have real world consequences are a good way to motivate for that. So here's an example of in the classroom, let it fail in a controlled manner. So I've done this exercise in the course that I teach that's called Workflows for Data Science. In this course, it's a project-based course, but we have to teach them all the skills so they can do a reproducible data analysis. And at the end of the course, one of the things that we get them to do is to make their compute environments for their analysis reproducible using a tool called Docker. Docker is not an easy thing to teach or learn. It's a lot of overhead. You're teaching, we need to teach them to write Docker files, writing how you install things in Linux, and half of the students are Windows users. So like there is a lot of, barrier and stickiness to teaching this subject. So you really need to motivate it. So one way that I do this in a demonstration is that we give students a data analysis project pipeline on GitHub, and we ask them, go to that GitHub repository, read the instructions, and try and replicate the analysis. Our students already have some Git skills at this point in the course, so they're able to do the Git clone, they're reading the README, trying to follow along with the instructions to run it. In the first instance, we've given them an analysis, and we've intentionally put in a lot of packages that we know they don't have installed. Like we've gone off into CRAN or into PyPI and found some very bizarre packages. We don't even necessarily use them, but you just tuck them in there. And if you want to be really, sneaky, you tuck them in there in the middle of the script, so they're not even at the top of the scripts. And you ask them to work on getting that analysis to run. And it takes some time, and eventually they figure it out, but it's frustrating. And then you give them the same analysis in a different GitHub repository, but you give that it has Docker solution. So there's a Docker image that exists on Docker Hub. The README gives clear instructions on how to run it and replicate the analysis, and they're able to do this they're able to replicate the analysis in a couple minutes. So this is an example of how you can let them fail in a controlled manner, and then at the same within the same learning time period, give them a solution and motivate them to that solution. And then they're in a good mind frame that even when learning Docker is hard and challenging, they have the motivation to learn it because that they know that their analysis is going to be more useful for other people afterwards. Okay, so the second thing that I said was important is direct instruction. So why is direct instruction important? Well, I think for those of us who've been using reproducibility tools in our research, what I'm going to say here is probably not new to you, but reproducibility is not something that most people or students figure out through exploration and inquiry based learning, or if you do, it's not an efficient way of doing it. There's a lot of, we're using a lot of borrowed tools from software engineering that are being repurposed for science and reproducibility. And so a lot of the, getting up and getting started has a lot of assumed knowledge behind it. And there's not a lot of like clear and easy on roads to these things. And because, I think, and there's also, how would I say this? Just because it's still fairly new, I would say that there's not a lot of culture around it that's very common to like show people where these obvious on-ramps are. So and then there's the challenge of the tools that I talked about in the previous example. So I think, again, having some direct instruction is important. And I really love this excerpt from Roger Peng's blog post from a couple of years ago that he wrote on the theory of data analysis. And he writes here that there is no need for a new data analyst to learn about reproducibility from experience. We don't need to lead a junior data analysis down a months-long winding path of non-reproducible analysis until they are finally bitten by the non-reproducibility bug and therefore learn their lesson. We can just tell them, hey, in the past, we found it useful to make our data analysis reproducible. Here's a workflow guide for you to use in your own analysis. Within that one statement, we can compress over 20 years of experience. We, I think, owe it to our students to directly instruct them with like the best practices that that the reproducibility community has arrived on to date, and then show them how to use these tools explicitly. So how do we use direct instruction in the classroom? So we do a lot of live demos. So in the programming classes, we do live coding to show how to use R and Python. But then when we're talking about other tools like Docker, R Markdown, or Jupyter for doing reproducible reports, using version control with Git and GitHub, we do a lot of live demos with those tools as well. And in doing that, it makes it, I think, more obvious to the students of like how to use these things, number one. And number two, you make mistakes, and that humanizes the experience of working with these tools that are somewhat challenging, because students make mistakes too, and they see that the experts are also making mistakes. And then you're able to usually make your mistakes where things are a little bit more difficult or are a little bit more sticky. And it gives you more time to spend on that area of the topic and explain why you made the mistake and where the misconceptions come in and fix them. The other thing that we use are guided worksheets and tutorials. So there's us giving the live demos, which is useful, but you can't, for all the time be up in front of people. And it's good for people to work through and actively engage with material themselves and get a little bit of practice, but not, in a totally like free-for-all, do your own thing, whatever you think is best, but in a guided way. So we have a lot of those in the program. But one thing I want to say is be careful when you there are some dragons when you teach this stuff. So because we're teaching things that involve graphical user interfaces, because we teach things that are coming from software engineering, it's a very fast moving field, and which means that every time I teach this stuff, I need to go through it before I send it out to the students, because something has changed and something has broken, and I have to come up with a workaround. So a story from this past term is that GitHub, which is the largest code hosting repository in the world, decided to, I think very rightfully so, change the name of their default branch. They switched it from master to main. But that caused lots of things to break. That caused all of our notes to have to be rewritten. And it's still like a half solved problem because we have a whole bunch of resources that are still sitting on master branch that we haven't been able to or will not be able to quickly change over. So it is really important to have this direct instruction, but these are things that you're going to have to kind of do new in the classroom every year. Make a new demo every year, curate your worksheets and your tutorials every year, because otherwise they're going to quickly fall out of usefulness. An example of direct instruction for teaching version control. So we teach version control in our very first year Introduction to Data Science course. And so we do this in kind of like a three-pronged approach for directed instruction. So we give them a textbook reading that they're able to use. This is something we have to update every year because the graphical user interface that we choose to use changes. We don't teach the command line for this in the first year because it's a bit too overwhelming, I think, for the students. Then we do a live demonstration where they watch us use the GitHub website. They watch us use the Git GUI. They watch us move files and add and commit and push and pull. And then finally, they work through a guided worksheet that asks them to do the same thing that we just did, and then ask them questions along the way to test that they like really understand like what is committing, what is adding, what is pulling, what is pushing, where is the work going. And if folks are interested, I have some links embedded in this talk that will take you to some of the examples or resources that I'm talking about here. Okay, and so the final thing that I said is lots of practice. So why do we need lots of practice for reproducibility, for learning reproducibility workflows and tools? Well, there are really two fundamental ways that we commit things to long-term memory. One is one trial learning, and that usually requires some sort of emotional impact. So that's like, sometimes it's traumatic events, and sometimes it's really good, positive emotional events that you had, like a really great birthday or your wedding or something like that. You don't need those things to be repeated multiple times so that you remember them. But that's not most of the things in school. Most of the things in school we learn about are through this repetitive space training. And so the best way to commit something to long-term memory that's not really emotional is to revisit it and repeat it multiple times and have breaks between those things. And so that lets you commit it to memory. However, I think you want to go even a step further with reproducibility because when we teach reproducibility workflows and skills as instructors, we actually want students to do more than just learn about these things. We actually want them to use them and put them into practice in the classroom, outside of the classroom, in their work after the classroom. And so we actually want to change their habits or behaviors. And it's quite, I think, important to realize that, okay? It's not just understanding an algorithm. It's understanding the concepts behind something like version control, understanding the concepts behind something like a shippable and shareable compute environment, and then knowing how to use those things. And then once you leave the classroom, wanting and being able to use those things without like saying, no, that's too hard or too tricky. You want them to just do it out of habit because that's what they usually do. So an aside, just a little, if people are interested, a book that's really recently made me think about more how we can tangibly do this is called Atomic Habits by James Clear. He's done a really good job of like bringing the science of habit building and behavior change into an accessible book. And I think that when we think about getting students practice and changing their behavior with reproducible skills and workflows, there's a lot of really interesting insight from behavior change and psychology and habit building that we can borrow. So now I'll talk more practically about, so at least right now, what are we doing in the classroom to embed lots of practice? So what we do is when we do our live demos, we don't just have us do it. Then we pause and say, okay, students, your turn. Do what I just did. And so they saw it, and then they actually have to type it into the keyboard or click their mouse around the graphical user interface. So they practice it that way. Then we have lots of low stakes assessments with small or short problems. So we've moved into a lot of flipped classroom. at UBC, or at least in the data science. So our introduction to data science course is a primarily flipped classroom. So we have literate code documents that have automated tests in them that the students are answering all kinds of questions about the data science content. And then they're very short little pieces that are well guided, but they get immediate feedback. And these things aren't worth very much, and they do a lot of them. So they do 2 of them a week in the data science course. In the Master of Data Science program, we've also started implementing this in some of our classrooms. And the students really like this practice, and it helps them really prepare for things like larger assessments like quizzes and their lab homework. But it gives them lots of practice. And then the other thing that we do is the learning technologies and platforms that we use are built and use authentic data science reproducibility tools. And so I'll give an example of that now. So in almost all of the Master of Data Science courses, so I'm talking about 20 courses here, 21 credit courses, so 21 month-long courses, we use version control, particularly GitHub, as our course management system. So the homework instructions and assignments are distributed to the students as GitHub repositories. And the only way that they can submit their homework is by putting their homework in that GitHub repository. So they have to go through the cloning procedure, or at least be able to somehow download this from the GitHub website. And then they have to be able to, hopefully through things like pushing and committing, send their work back to GitHub, but they would at least have to interface with the GitHub website to do this. To try and incentivize actually using the Git machinery to interact with GitHub, we also put part of the marks of each of these assignments as to mechanics. And so we need to see, for example, like 3 commits associated with every single assignment, because we think, we're trying to build these good habits and practices around, like, there's reasons why you use version control, not just to submit your homework, but to act as a backup, or in case you want to go back in time and change things. So by the end of this program, the students have version controlled their work in over 80 different repositories. So they have so they're very practiced and very used to it. And they're basically, you want them to be able to do it in their sleep, almost. And so that when they leave the program and they go to work somewhere else, it's just natural. It's just one of their habits at this point, that if they're going to work on a project, it's going to go under version control. So we do this using tools, and here I've listed, and there's many tools now, which is pretty cool. We're not the only program doing this at all. There's many tools now for using GitHub as a classroom learning management system. And so I've listed a couple of them here if folks are interested. So with that, I'm going to wrap up so that I have some time to answer some questions if folks have them. So we think over the past 5 years from teaching in the Master of Data Science and our Introduction to Data Science course, that key things for teaching reproducibility in the data science classroom are providing extra emphasis on motivation, providing direct instruction, so it's not a mystery of how you get started and what you need to do, and lots of practice, so that we can not only teach them the material and the concepts, but so that this actually changes their practices and their workflows, and they will use it after your classroom. So I'm happy to take questions now here, or you can tweet to me on Twitter, and I'm happy to answer there. And again, I've posted the link for the slides.
Thanks very much, Tiffany. Amy, did you want to chair the question period, or shall I?
I can. I'm just going to check the thread. I don't see anything right now. Anyone have anything to start off with?
I have some if there's none. Otherwise, maybe Mina has comments. I'd love just to have Mina and Tiffany just tell us everything you know between the two of you. Was there something that you started doing that I mean, obviously it's an evolution, right? All of these programs are just in the evolution stage. Was there something that you started doing that you've really moved away from?
Yeah, I would say the pandemic's even placed a greater emphasis on this. So when we started teaching the Master of Data Science program, we had a small cohort and we were in person. which allowed us to provide a lot of support. But as you scale these things, having that intimate, close support is more difficult. And so in the very first year of the program, in the MBS program, we have like we have this philosophy that they should be able to be somewhat experts of running stuff on their laptop. We do teach them some cloud tools, but you should be able to install your software stack and be able to set up your path and these sorts of things. And so we have a pretty, I'd say, like intensive list of like 20 things that they need to install in the first week. They need to use Git to submit their homework in the first week. And it's a bit overwhelming and it's a lot. And so what we've kind of like eased off on that and moved we get them there, but we take longer now to doing that. So we've set up this year a Jupyter hub to have them work in a cloud-based setting for the first week or two. And then after the first week or two is when we transition them to their own laptop, so that we give time for the expectation that setting up everybody's system is going to encounter some bugs and take some time, and that's going to be tricky. We've also, for the first assignment, we no longer ask them in the first assignment to submit to GitHub. That's assignment 2, so that we have to give ourselves like a week or two to get them up to speed for Git and GitHub. And so I think that that sort of thing has definitely changed and been inspired with. So first I started working in the Master Data Science program, and then I started teaching undergraduates, and teaching undergraduates has made me have to reframe things and think about things differently, and think about like, how do I remove barriers so that people, maybe people who are for whatever reason more sensitive to not feeling like data science is for them, I don't want them to drop my class because they couldn't install something. So I think, yeah, that's something that's changed a lot.
I'll just quickly get to Mina's question where she needs to go. A question about, have you seen any changes in computing experiences of students applying to your MS program? Are more students coming in with familiarity with these tools, or not yet?
Yeah, that's a great question. I do a little survey every year about like in the first class, I'm like, what tools have you used before? And usually about half of the students have used R, maybe 3/4 of the students have used Python. Almost all of them have seen Jupyter. Almost none of them still have seen Git and GitHub. So it's really quite amazing that computer science programming prerequisite. So they don't have to have had R or Python before. But yeah, it's still interesting that even though I'll comment in a second that we are seeing people with more technical or data science skills coming to our program, it's still the experience with reproducibility related tools are aside from Jupyter, like not as present as one might expect. I am seeing more and more people having like a graduate in data science applying to our program, which is something kind of new and interesting for us to think about, because our program was really designed not for somebody who is like a data science undergraduate, like somebody who had an undergraduate in a different discipline and wants to then apply, data science to their discipline. So we're still thinking about like how we're going to handle the change of like, there's going to be more and more undergraduates coming in with this expertise.
Yeah, it's a super interesting problem. John's asking, what do you do with Docker and Windows? Is there something special about Docker and Windows?
Yeah, so it can work, but everything with Windows is a little bit more challenging. So what my strategy is I have, I'm a Mac person, but I also have a separate PC laptop where I have Linux and Windows installed, so that before I teach every course, I go through and make sure that I know how to install things on Windows and what instructions to provide to students. There's still always surprises. One thing, we do this on quite a large scale, largish scale with the master students, but I'd say like we're dealing with 50 or 60 different Windows laptops every year. And so to make our lives easier, we've been really tightly restricting which version of Windows that they have, because then it's easier to know. So we say you have to have Windows 10, you have to have this build, and it can't be Windows Home. Basically, it has to be Enterprise Pro or Education. And by doing that, that has reduced some problems. But every year, something new comes up. Like I can just tell you this week, I'm teaching Python packaging with poetry, and Git bash doesn't work with poetry anymore this year. It worked last year, but it doesn't work anymore. There's a GitHub issue open, it's not resolved. So now we're using Anaconda prompt on the Windows machines. We have a solution, but it's one of those, there will be dragons in this field.
Yeah, changing things is just so much work, right? You think you're done, and then at least 20 years ago, right, the folks, they write out their theory equations and that was it. They were done for the next 20 years. We've got to update our softs every 6 months. Did you have any other closing comments or thoughts that you wanted to say?
I don't, yeah, not so much. Just really thank you very much for inviting me to speak here. It was a lot of fun, and I'm looking forward to the remaining talks.
Yeah, no, thank you so much for speaking, Tiffany. Really appreciate it. And it was just fascinating to hear what you're doing. As I think you're largely forging the path that I think we're traveling at Toronto as well. Thanks very much.
Thanks.
And next, Tyler, are you around? Yeah, Amy, did you want to introduce Tyler?
Sure.
Yeah. Okay.
Yeah. Okay. So I'm happy to introduce our next speaker. Tyler Gerard is a PhD candidate in political science at the University of Western